The section below is subjected to a shear force of 80 kilonewtons. Draw the shear stress distribution for the section. Welcome, ladies and gentlemen, as we solve this problem. Now, the diagram that we have here is an I-beam section of a beam whose top flange and bottom flange have got different breadths. The top flange have got a breadth of 25 centimeters and the bottom flange have got a breadth of 15 centimeters. Now, the first thing we are going to do is to locate the position of the neutral axis. And for us to locate the position of the neutral axis, we are going to use this table that have got the component, area, centroidal distance y from the bottom edge of the flange, and then we have a y. We have three components, that is the top flange, we have the web, and we have the bottom flange. Now, the top flange, its center of gravity should be here, call it G1. The web, its center of gravity, I guess at that point, that is the center of the component itself, so that is G2. And the bottom flange, we got G3. Therefore, on the component end, we have component 1, whose area is breadth times its depth. And therefore, that is 25 multiplied by 5. And 25 multiplied by 5 is 125 square centimeters. On the other hand, the second component, that is the web, have got an area of breadth of, this should be 5 centimeters, that is the thickness. The thickness of the web is 5 centimeters, therefore we got a breadth of 5 centimeters multiplied by a depth of 25 centimeters, giving us an area of 125 square centimeters. Then finally we have the third component, whose breadth is 15 centimeters and a depth of 5 centimeters. And that is equivalent to 75 square centimeters. Therefore, those are the areas of the three components. Now, the centroidal distance y from this lower section of the bottom flange will be 5 centimeters plus 25, that is 30, plus 2.5, that is 32.5. Therefore, we have 32.5 centimeters centroidal distance y of the first component. For the second one, we have 17.5 centimeters. And for the third component, that is the lower flange, the distance from LL to G3 will be half of 5, which is 2.5 centimeters. Good. Then from there, we multiply area times y. 125 times that 2.5, that is 4062.5 centimeters raised to the power of 3. 125 times 17.5, that is 2187. 2187.5 centimeters raised to the power of 3. And 75 times 2.5, that is 187.5. Therefore, That's all we have. Now, from there, we are going to add AY. Therefore, summation of AY is going to be 6437.5. So we have 6437.5 centimeters raised to the power of 3. And summation of area is going to be 325. 325. Therefore, bar Y is going to be summation of AY divided by summation of A. Summation of AY is 6437.5 all over summation of A, which is 325, and that's going to give us bar Y being 19.8 centimeters. 19.8 centimeters. Therefore, when we input it here, going to have 19.8 centimeters, and the remainder, that is 35 minus 19.8 centimeters, that is going to be 15.2 centimeters. So when you try to locate it, I had pre-located it, and it's going to be at this point just above G2. Remember, G2 is 17.5, therefore 19.8 is just above that. So this is where the neutral axis passes. Now, after locating the position of the neutral axis, the next thing will be determining the moment of inertia about the neutral axis of this I-beam section. And for us to get the moment of inertia about the neutral axis of this section, we are going to add the moment of inertia of these three components about the neutral axis, which will give us the summation of the moment of inertia of this I-beam cross section. And therefore, Ixx will be given by Ixx1 plus Ixx2 plus Ixx3. Now, starting with Ixx1, this is going to be BD cubed over 12 plus its area into bar Y is 19.8 and Y is at 2.5, therefore into Y minus bar Y squared. And this is going to be the breadth Ixx1, that is the moment of inertia of the top flange about the neutral axis. Therefore, that's going to be its breadth 25 centimeters, its depth 5 cubed divided by 12. Add this to its area, 125 centimeters into Y 32.5 minus bar Y 19.8 squared. Now, Y minus bar Y is this distance, that is from G1 to the neutral axis. And therefore, this is going to give us 20,421.67 centimeters raised to the power of 4. Ixx2 will be given by BD cubed over 12 plus area into bar Y minus Y, and then we square it. And this is going to be equal to, the breadth of the web is 5 centimeters. Therefore, we have 5. The depth is 25 centimeters cubed. Divide this by 12 plus the area of the web is 125 square centimeters. By y is 19.8 and y is 17.5, and then we square that, and this is going to give us 7,171.67 square centimeters raised to the power of 4. Finally, the moment of inertia of the third component, that is the bottom flange, that's going to be BD cubed over 12 plus area of the bottom flange into bar y minus y squared. That is this distance from the neutral axis to G3. And that's going to be the breadth of the bottom flange 15, depth 5 cubed, divide by 12 plus the area is 75 square centimeters into by y 19.8 minus y 2.5, and that is squared. And this is going to give us 22,603 centimeters raised to the power of 4. Therefore, that is the value of Ixx3. Now, for us to get the moment of inertia about the XX axis of the whole I-beam section, we are going to add Ixx1 plus Ixx2 plus Ixx3, and that's going to give us 50,196.34. 50,196.34 centimeters raised to the power of 4. Therefore, that is the moment of inertia about the neutral axis or about the XX axis of this I-beam section. Now, after getting the moment of inertia, the next thing will be determination of the shear stresses, that is, at the junction between the top flange and the web, the shear stress at the neutral axis, which in this case is maximum. Remember, shear stress is maximum at the neutral axis, as well as the shear stress between the junction of the bottom flange and the web. And we are going to begin with the shear stress at the junction just between the top flange and the web. And that's going to be shear stress will be equal to S A bar Y divided by IB, which will be the shear force. S is the shear force, 80 kilonewtons, multiplied by the area of the top flange. We are going to convert centimeters to meters because the SI units of stress is kilonewtons per square meter. Therefore, we are going to convert centimeters to meters. So the area of the top flange is 0.25 meters. 0.25 meters, times the depth 0.05 meters into, now bar y will be the distance between G1 and the neutral axis, and that will be given by 15.2 centimeters minus half of the depth, which is 2.5, and that is going to be 0.152 minus 0.025. Then we divide this by IB. I is the moment of inertia about the neutral axis of the entire I-beam section. Now, when we convert it to meters raised to the power of 4, we are going to have 5.0196 multiplied by 10 raised to the power of -4 times the breadth of the top flange is 0.25, and therefore that's going to give us a shear stress of 1012.03 kilonewtons per square meter. Therefore, this is the shear stress at the junction just between the top flange and the web, this junction. Now, the shear stress at the junction of the web and the flange, that is shear stress in the web, just at the junction between the web and the top flange, is going to increase abruptly. Therefore, this is shear stress in the web. It is going to increase abruptly from 1012.03 kilonewtons per square meter times the breadth of the top flange, which is 0.25, divided by the breadth of the web, which is 0.05. In this case, we can say B divided by B. So that will be an abrupt increase in shear stress just between the junction of the web and the top flange. And this is going to give us 5060, that is 5060.164 kilonewtons per square meter. Therefore, that will be the shear stress in the web just at the junction between the web and the top flange. Now, from there, we go to maximum shear stress. Maximum shear stress. Now, the maximum shear stress, as we said earlier, will occur at the neutral axis, and it will be given by, so this is maximum shear stress, it will be given by SA bar Y divided by IB. In this case, small b, the breadth of the web, because the maximum shear stress will occur in the web. Now, A bar Y will be given by the moment of area of the flange about the neutral axis plus the moment of area of the web about the neutral axis. Now, the moment of area of the flange about the neutral axis will be given by, therefore we are going to have A bar Y for the flange, that is the moment of area of the flange about the neutral axis, plus A bar Y for the web, that is the moment of area of the web about the neutral axis. So we can call this summation of A bar Y. Now, A bar Y for the flange, A bar Y for the flange will be given by the area of the flange, which is 0.25, that is the breadth, times its depth, 0.05, times bar Y is the distance from G1 to the neutral axis, which in this case is 15.2 minus 2.5, which is half the depth of the flange. So that's going to be 0.152 minus 0.025. And A bar Y for the flange, that's going to be 1.5875. 1.5875 times 10 raised to the power of negative 3 meters raised to 3. So that is A bar Y for the flange. On the other hand, A bar Y for the web will be given by the area of the web, that is the breadth 0.05 multiplied by its depth 0.25 times bar Y. Now, for the web, we are considering this section between the neutral axis and the junction, and this depth of this web section above the neutral axis is going to be given by 15.2 minus 5, which in this case is 10.2 centimeters. And therefore, its center of gravity will be given by half that depth. And so, we are going to have bar Y for the section of the web 0.102, that is converting centimeters to meters, divide this by 2. And this is going to give us, so when we multiply A bar Y for the web, that's going to give us 2.601 times 10 raised to the power of negative 4 meters raised to the power of 3. Therefore, that is A bar Y for the web. And therefore, summation of A bar Y, that is A bar Y for the flange plus A bar Y for the web, is going to be 1.8471 multiplied by 10 raised to the power of negative 3 meters raised to 3. That is, when we add A bar 1 for the flange plus A bar Y for the web, we are going to get this. Therefore, the maximum shear stress for the entire I-beam section above the neutral axis will be given by S, that is the shear force of 80 kilonewtons, times summation of A bar Y, which is 1.8471 times 10 raised to the power of negative 3, divided by the moment of inertia about the XX axis, which in this case is 5.0196 times 10 raised to the power of negative 4 times the breadth of the web, which is 5 centimeters. In meters, that is 0.05 meters. And therefore, the maximum shearing stress about the neutral axis will be equal to 5887.64 kilonewtons per square meter. So that is our maximum shearing stress. Now, after getting the value of the maximum shearing stress, we now go to the bottom flange, that is calculating the shear stress at the junction of the bottom flange and the web. Now, the shear stress in the bottom flange just at the junction between the bottom flange and the web will be given by S A bar Y divided by IB, which will be equal to shear force of 80 kilonewtons times the area of the bottom flange, which will be breadth of 0.15 times a depth of 0.05 into the distance from G3 to the neutral axis. That's going to be 19.8 minus 0.25. That minus 2.5. That is half the depth, and therefore that's going to be 0.198 minus 0.025, and therefore the shear stress is going to be 1378.6 kilonewtons per square meter. Now, the shear stress in the web just at the junction between the web and the lower flange will increase abruptly from 1378.6 multiplied by capital B, that is the breadth of the bottom flange, 15 centimeters, which is 0.15 meters, divided by small b, that is the breadth of the web, which is 0.05 meters. So in this case, we can talk of B over B. And that increase will be equivalent to 4135.788 kilonewtons per square meter. Therefore, this will be the shear stress in the web just at the junction of the web and the lower flange at that point. Now, after getting the value of all the shear stresses, the next thing will be drawing the shear stress distribution diagram for this I-beam section. So join me so that we see how to plot that shear stress distribution diagram for an I-beam section whose top flange and bottom flange have got different breadths. Now, plotting the shear stress distribution diagram, I have written all the shear stresses at that point so that I get adequate space for plotting this diagram. And this is how we are going to plot it. We have the upper edge of the top flange. We have the junction of the top flange and the web. We have the neutral axis. We have the junction of the web and the bottom flange. And then we have the lower edge of the bottom flange. Then we have the origin line, the vertical line. And we already know that the shear stress at the edge at the top and bottom edges of the I-beam section are 0. Therefore, the shear stress here is 0 as well as at this point. Now, the shear stress in the flange at the junction of top flange and the web is 1012.03. Therefore, approximately that point. And so I will draw a smooth curve connecting to that point. Then this 1012.03 increases abruptly to 5060. Therefore, 5060, approximately that point. Then from there we have the maximum shear stress. So therefore, if this is 50, 60, 58, 87, maybe at that point, again, we plot a smooth curve connecting that point. Therefore, we have the maximum shearing stress. Now, when you come to the lower fringe, the shear stress at the lower edge is 0. Then the shear stress in the flange just at the junction of the lower fringe at the web is 1378.64. So 1378 is approximately that point, which increases abruptly from 1378 to 4135. 4135 maybe at that point. Therefore, we are going to join the 0 shearing stress to the stress at the junction of the lower fringe and the web, which is 1378, increases to 4135, and then we join that with the maximum shearing stress with a smooth curve. And therefore, ladies and gentlemen, that is now our shear stress distribution diagram for an I-beam section whose top and bottom flanges have got different dimensions. And in this case, our top and bottom flanges have got different sizes of their breadths, though their thicknesses or their depths are the same. Now, we have to light these shear stresses on our diagram, and this is how we are going to light them. This one is 1012.03 units, and then increases to 5060.164 units. Then the maximum shearing stress is 5887.64 units. 0.64 units. And then here we have 1378.64 units. Then it increases abruptly to 4135.788 units. Therefore, ladies and gentlemen, that is how we plot a shear stress distribution diagram for an I-beam section whose top and bottom flanges have got different sizes. Thank you for watching our video. Please subscribe to our channel, give us likes, give us comments, share our video to your friends, and you will make this channel move to the next level. Thank you very much.